folks. All right, well, this time we want to take a look at subroutine abstraction. So kind of our objective now is to say, if I have to model in this sort of intermediate abstract representation, everything associated with a function call or a procedure call and return, how am I going to go about doing that? Keeping in mind that we've got to deal with parameters, we've got to deal with the scoping issues, we have to deal with things like pass by value or pass by reference, we have to deal with return types. So all of these things have to be modeled somehow, and that's what we want to take a look at right now. So have a bit of a play with this. So the idea of having these sort of lexically scoped subroutines has been part of most programming languages since the late 50s. Algol was actually a really interesting language that came out in the late 50s, and it was never really used in a practical sense, but it became sort of the ancestor for a lot of other programming languages just because of some of the ideas that it introduced. It introduced the idea of having blocks of code that had a begin and end statement. It introduced the idea of lexically scoped functions. It introduced the idea of using formal grammars to describe your language. So there were a lot of things that came out of Algol that have been used pretty much ever since. Anyway, going off on a tangent here, but the idea is, again, we need an effective approach to model these things within our intermediate representations, right? In pretty much any language that we're trying to represent. The other problem is that we need to take into account the idea that a function might be declared in one file, for instance, and used in another one, and the two files might be compiled separately. So when you're compiling the one that's using the function, you don't actually have the implementation from the file that declared it. And in the file that declared it, you don't have the examples of the calls to it. So this is something that we have to think about in terms of our compilation models, because it is something that is, again, extremely widely used. If you want to use a library function, the odds are it's already been compiled. If you want to develop large systems, the odds are you're compiling the individual components separately and then somehow linking them together. So we have to be able to define and declare items in one compilation unit and yet refer to them in another and still do our reasonable runtime or compile time checking of these things. So in terms of just looking at the sort of procedure call itself as this abstract entity, when we go to call a function, right, the caller calls the callee, invokes the callee. Somehow we've got to preserve anything relevant about the caller's environment, right, to make sure it doesn't get trashed by the callee. We've got to take the data that we're trying to pass from the caller to the callee, and they've each got their own namespace. So I've got to try and find some way to map the names and values and data elements in the caller's namespace to the namespace, to places in the callee's namespace where it can access them and use them. And of course, we've got to set up the callee's environment, run the function or run the subroutine, clean up that environment afterwards, and on return, possibly return one or more values from the, I've got that backwards, from the callee to the caller. We've got to restore the caller's environment, and then we've got to resume execution at the spot immediately after the call from the caller. So these are kind of the key steps that we want to think about and deal with as we're trying to set this up, as we're trying to model our subroutines. And again, the idea is each subroutine has its own little local space, right? Its own new protected namespace, if you like. And when we're using, or when we're referring to variables or items within our subroutine, the idea is that local declarations take precedence over the external ones. So if I declared an X inside my subroutine and I say do something with X, I mean the one that I declared in my subroutine. We need some form of parameter passing mechanism generally to map data, again, from the caller's namespace to the callee's. And those mappings, right, whatever we're doing for our parameter handling, need to support the different addressing modes that are relevant to the language. So pass by value, pass by reference, whatever that might be. Usually in terms of handling these ideas like separate compilation, there has to be some standard, some convention, some agreed upon way for doing this. And the idea is that people who are developing the compilers have to agree with the people who are designing the language and come up with this convention. So usually this happens pretty early in the language design process, where you nail down, okay, this is how the division of labor is going to take place when a function call is made. This is how things are going to get passed. This is how things are going to get returned. This is a convention that we're going to stick with. And you need that convention to make sure that when you go off to call a library routine, whoever set up the library routine has it working in the same fashion as you're coming up with. So these are things that we need to nail down in advance. And we'll talk about some of the different ideas on some of the different possible sequences we can go through and how we can divide the responsibilities up between the caller and the callee when it comes to setting things up and tearing things down. So the compiler itself, when it's going through, it has to think about, okay, when I'm compiling a program, what does the space for things like global or static variables look like, and where's that going to exist? For any individual function call, what's the space for that function call going to look like? Again, if we're thinking in terms of a stack, what's that stack frame going to look like for that function call? Now, the things that are done globally or statically, we can figure out at compile time and say, okay, well, if our program gets loaded into memory at this address, or at least if the global memory space gets loaded in at this address, then here are the offsets to each of the locations for each of the different global variables or each of the different static variables. So the compiler can lay out all of the global information, come up with addresses based on an offset from wherever this thing's going to wind up loaded into memory. For local storage layouts, though, for the layout for a function, let's say, that winds up on the stack someplace, obviously that space isn't going to get created until runtime, when that function actually gets called. So what the compiler has to do is figure out what the mapping would look like, how much space is set aside for the return variable or return value, how much space is set aside for the parameters, how much space is set aside for the local variables, what order are they going to be in that space. And it has to generate the code that will get executed on a function call to actually create that space and insert all of the values in the correct spot, and then clean it up again afterwards. Right, so the compiler is going to have to generate the code. It's going to have to come up with a template for what the layout's going to look like, and then generate the code to actually populate that at the point of call and clean it up at the point of return. So we'll get into the gory details on this as we get into actual code generation in another couple of weeks. Now, in terms of keeping track of the information for any individual function call, again, we're going to try and keep a kind of abstract view of things here. So we're going to refer to these as activations. Each call is an activation of that function, and we'll refer to the data that's stored for that activation as an activation record, right? Just to come up with some terminology for this. So for each of the different active calls right now, so if function f calls g and g calls h, then at the moment all three of them are active and h is the one that's currently running. The compiler has to maintain the activation records for all three of them, right? You need that information because when h completes, we've got to go back to g's and use that. When g returns, we've got to go back to f's and use that. So we've got to make sure that we can keep this information available and that we can return to it as we need to. So the typical model is, of course, our kind of stack-based, where we're pushing all these frames on the top of the stack as we call functions, then popping them off as we return. So a pretty typical approach would be, say, okay, let's save the caller's environment on the stack somehow, push some space for the return value, push some space for the parameters, push those actual data values, push some space for the local variables. And who takes care of this, whether this is taken care of in the code generated for the caller or the code generated for the callee, is something that we still have to figure out. but those are basically tasks that have to take place at the point of the call. So maybe in terms of dividing up the responsibility, again, we'll try and figure out when the call is made, what does the caller do, and then what does the callee do? And when the callee completes, what does the callee do to clean up, and what does the caller do to clean up? Hopefully all of this stuff kind of rings bells from your 261 days, your your digital logic days, but or pardon me, your computer architecture days. But again, the pretty typical sequence is to say, well, if I've got a bunch of data in registers that the caller is using, I don't want those trashed by whatever the callee does, so maybe we say it's the caller's responsibility to preserve the registers that they want saved. Then if we're doing any pass-by value, we've got to evaluate those actual parameters and push those results on the stack somehow. We have to figure out and set up space for the return address. Maybe we do these in the other order, but again, both steps have to take place. If we've got some pass-by reference parameters where we're passing the memory address of things, I want to make sure that those parameters are actually in memory at that address. Right? So if I'm doing things like moving stuff back and forth between memory and registers, I want to make sure that the current data is actually in memory right now, so that when I pass that memory address, that the correct thing is getting updated. And again, set up the parameters that we're passing. We've got a little bit of duplication here, but again, the idea is we're figuring out what responsibility the caller has before we actually make the call. Then we fire up the callee, and in the code that's generated for it, there's got to be stuff to, let's say, set up the local variables, assign any local variable values, right? Set up the space on the stack. Maybe we're going to do some rearrangement of the registers based on what parameters and what local variables we want where. And then go through and actually execute the code for the function we've called or the subroutine we've called. And then when that completes, we need to kind of reverse this process. So delete any locally allocated space, restore any registers that we were mucking with. Again, care needs to be taken between the two of them to make sure that you're actually covering everything that needs to be saved and restored. Put the return value wherever it needs to be, and then return control to the caller, for instance. And then at that point, the caller would take over, and the code from the caller would say, okay, well, if there were pass-by reference parameters that I moved from a register to memory to make sure that it could do the pass-by reference, I'll move those back to the register if I need to. Capture the return value, deallocate the space that I put on there for the parameters, restore any of those registers that I preserved earlier, and then pick up execution at the instruction immediately after the function call. Right? So this would be one reasonable way to break down who's responsible for what. So when the compiler goes to generate the actual code for this, it's going to generate code for these pieces at the tail end of the caller right before the call. So this would be kind of our pre-call step. And then the first couple of steps in our caller would include the code to do that. The last couple of steps in the callee, the last couple of steps in the callee would be the code to take care of this. And then the first things that the caller does would be the code that actually takes care of these different steps. Right? So it just gives the compiler writers a blueprint for what they have to put where. Now, that's not the only set of options. We can take a more complex approach. Things like scheme will go through and pass an entire environment along with the subroutine. So, okay, here's here's the environment, the context in which this subroutine is supposed to run. And so we always run a subroutine in its own environment, right, in the context of its own environment. But that gets into sort of much more memory-intensive approaches, and time-intensive approaches for that matter, to passing all the relevant information. For the most part, we're going to focus on the kind of traditional, mostly stack-based approaches. Now, it does mean that we've got to be able to keep track of access to different variables and things across different lexical scopes. right? If we assume that we've got lexical scoping, maybe we take a kind of a C-ish approach where we've got global scope and we've got file scope and we've got function scopes. Maybe we're in a language that allows nested function declarations, so we've got a function scope inside a function scope inside a function scope. Again, block scopes, and it's pretty typical to allow nested blocks, and if we're allowing different scopes for different blocks, then we've got these different layers of nesting. So you can have quite a few layers of scope active at any given point in the program, right? If I'm in an if statement inside a loop, inside a function that's defined inside another function that's defined in my file, and there's some global variables that are cross-file, then we've got all of these different scopes that are currently active. So the compiler needs a way to refer to the items that are declared across the various scopes. So I just want to take a look at one possibility here. So one idea is to keep track of the active lexical scopes, and we'll give each of those scopes an integer, right? Starting from 0 at the outermost scope, the global scope, and we'll just go up by ones. So the file scope would be 1. If we're in a function, that's going to be 2. If we're in a block inside that, it's going to be 3. If we're in a block inside that, it's going to be 4. So we give each scope an integer identifier. And we'll assume that for each scope, it's got some block of local storage someplace. And so each variable, each defined item is going to be at some offset from the beginning of that local storage. So when the compiler wants to refer to a specific item, it's going to do so by specifying which of those scopes it's in and what the offset is from the start of that scope's storage block. Now, if we're doing this at the in our kind of intermediate representation, it does mean that we're making some kind of assumptions about the storage sizes for the different units, but it gives us a way to refer to these things, and we'll nail this down in a little bit more detail as we get into the actual code generation. So again, if we take an example where, and I'm going to assume that file scope and global scope are the same thing for this one. So let's say we've got a global variable x, we've got a function f that's got a couple of local variables in it. We've got a main routine, and here we'll allow a nested function declaration. So we've got a variable or a function g declared inside there after the declaration of some local variable y. So if I'm going through and referring to things, let's say from if I'm in my global scope and I refer to x, then x is the first thing in my global scope. So it's scope 0 and offset 0. Right? At the global scope, there is no y that exists, so I can't really refer to that. If I'm somewhere inside f and I refer to x or y, then I'm referring to scope level 1 and maybe an offset of, here I'm just assuming 4 bytes each for both ints and floats. An offset of 0 for x and then an offset of 4 for y. If I'm somewhere inside my function g, then the x would be referring to the one that's in g, and a y would be referring to the one that's in the main. So my scope level for that x would be 2, and in this case there's nothing before it, so it's just an offset of 0. And for y, it would be in scope 1, right, the main routine scope, and again an offset of 0. And if I was in the body of my main routine, then if I referred to x, that would have to be referring to the global one, so scope 0, offset 0. And if I was referring to y, it would be that local one, so scope 1 and offset 0. So you get this kind of structure of going through and having a scope and offset kind of reference. All right, the only other thing I wanted to bring up was a little bit of discussion on parameters and return values, and we'll get into more of this stuff when we talk about activation records next time around. But the idea is, again, we need to support all of the different addressing modes that our source or target language needs to work with. So most commonly, we're talking about pass by value, where we're just copying a value in, or pass by reference. Right? With pass by value, again, the idea is we go through, evaluate the argument, copy the value into the parameter storage space, and away we go. The only real concerns there are if we've got large data types to work with. If I've got this big array that I'm passing by value, then in theory I'm copying the entire thing into the stack space, which is of course going to be both time and memory intensive. So it's not unusual for languages to say, well, you know what, if it's a big data structure, I'll actually pass a reference to it, but I'll try and throw in some extra code within the code for the function itself that prevents them from actually altering the contents of that beast. So effectively making it a passing a pointer or passing a reference, but treating the thing as a constant anyways, a constant value anyways. So there are some things to think about with pass by value, but again, it's a fairly well understood mechanism. Or the other approach, pass by reference, where we go through and provide some kind of an access mechanism. So typically passing a pointer or a memory address to the item, specifying, okay, you can change this thing in memory. Now, as we mentioned earlier, this means that the thing actually has to be at that address, but as long as it's there, then we can insert the appropriate code in the generated function code so that every time it refers to that particular item, it goes to the appropriate address in memory. Or it follows the indirection mechanism that we've specified to get at that item in memory. So we'll get into a lot more of the gory details of this when we get to code generation, but we'll talk about most of these things again as we talk about the activation records themselves in the next section.